Hi, this is Professor V.K. Patil. I welcome you to the video classes on basic electronics. So in my last class we have discussed about the differential amplifier. Today we will see another application which is nothing but the adder circuit. So this adder circuit also called as summing amplifier. In the summing amplifier basically it adds the different input voltages. That is what output voltage is directly proportional to the sum of input voltages. So what is this circuit? The circuit is basically an inverting amplifier with multiple inputs. So we need to draw the inverting amplifier. So inverting amplifier where input is applied to the inverting terminal, non-inverting terminal is grounded. Supply voltages are plus Vs and minus Vs. Output voltage is V0, where we have the feedback resistor, let us say RF. The feedback is applied from output to the input through the resistor RF. Let us say this is the resistance R1. Now in adder circuit multiple inputs I need to apply, and these multiple inputs can be applied through the resistors. Let us say three inputs are applied, V1, V2 and V3. So these are the voltages V1, V2 and V3. Resistors are R1, R2 and R3. Now in this circuit we need to prove that output voltage is directly proportional to the sum of the input voltages V1, V2 and V3. To find the expression for this circuit, let us assume the current flowing through the R1 is I1, current flowing through the R2 is I2, current flowing through the resistance R3 is I3. The current flowing through the feedback resistor, let us say IF, and the current which is entering into the op-amp, let us say it is II, right? Then applying the KCL at the node X, apply Kirchhoff's current law at node X. What is the Kirchhoff's current law? Incoming current at any node, it must be equal to the outgoing current. The incoming current to the node X is I1, I2, I3. Outgoing currents are II and IF. So therefore the expression becomes I1 plus I2 plus I3. It must be equal to IF plus II. But what is II? II is nothing but the current which is entering into the op-amp, and we know that input impedance of a op-amp is very high. Hence the II must be a 0, that is current entering into the op-amp must be a 0, hence II must be the 0 as Ri is infinity. Infinity means it acting as an open circuit, and we know that the current flowing through the open circuit is always 0, hence II must be a 0. Substituting II is equal to 0 in this expression and writing these currents in terms of the voltages, we get I1, the current which is moving from the V1 to the node X, and we know that current can be written as potential difference divided by the resistance. What is the potential difference? V1 minus Vx, where Vx is the voltage at the node X. Current is moving from V1 to the node X, hence V1 must be a positive and Vx must be a negative, because the current always it moves from higher voltage to the lower voltage. Hence I should subtract Vx from V1, that is nothing but the potential difference. V1 minus Vx divided by R1 plus V2 minus Vx divided by R2, that is nothing but the I2, current I2, which is nothing but V2 minus Vx divided by R2, plus V3 minus Vx divided by R3, which is equal to IF. And what is IF? IF is the current which is moving from node X to the output. Potential difference, it becomes Vx minus Vout divided by RF. By using the concept of virtual ground, what is virtual ground concept? The voltage at inverting terminal must be equal to the voltage at non-inverting terminal. Non-inverting terminal is grounded, means what? The voltage at this terminal is 0. This voltage must be at X also, because X is the voltage at terminal inverting, right? So therefore Vx must be equal to the 0 by using the concept of virtual ground. Is it right? So therefore substituting the Vx is equal to 0 in this expression, we will get V1 by R1 plus V2 by R2 plus V3 by R3, which is equal to minus V0 divided by RF. Right? Simplifying this expression, we will get V0, which is equal to minus RF by R1 into V1 minus RF by R2 into V2 minus RF by R3 into V3, which can be written as minus RF by R1 into V1 plus RF by R2 into V2 plus RF by R3 into V3, which is equal to V0. Now, if I consider R1 is equal to R2 is equal to R3 is equal to R, then the expression becomes V0 is equal to minus RF by R inside the bracket V1 plus V2 plus V3, which indicates that output voltage is directly proportional to the sum of input voltages. That is why this circuit is known as adder circuit, where output voltage, it depends or it is directly proportional to the sum of the input voltages. This is nothing but adder circuit or the summing amplifier. So this same circuit, it can be also used as scaling amplifier. How? Let us see this. From this expression, let RF by R1 is equal to A, RF by R2 which is equal to B, RF by R3 which is equal to C. If I consider these values, the output voltage, it becomes equal to minus A into V1 plus B into V2 plus C into V3. This is nothing but the output voltage. Here A, B, C, these are the scalar values. Hence I can consider that the same circuit as scaling amplifier also, where the V1 is multiplied by the scalar A, V2 is multiplied by the scalar B, V3 is multiplied by the scalar C. The same circuit, it can be used as a scaling amplifier. So in this class we have discussed a summing amplifier, which can be also used as a scaling amplifier. In summing amplifier, the output voltage is directly proportional to the sum of the input voltages, whereas in scaling amplifier, the input voltages are multiplied by the scalar quantity. That scalar quantity A, B, C can be chosen simply by choosing the proper values of R1, R2, R3 and RF. This is all about the summing amplifier as well as the scaling amplifier. Thank you. In my next class, we will see some more applications.